Hello everyone, I'm Sashank, a third year student from BITS Pilani. Uh, Today, as a part of blockchain technology course, we'll be seeing what are the second layer scalability solutions of blockchain technology in about 20 minutes. Let me introduce to the topic so that we are all on the same page. In the history of crypto, there have been three instances where the gas fee on Ethereum spiked to astronomical heights, like the bull run of 2017, the DeFi summer of 2020, and the NFT summer of 2021. So every time gas price increased, a more pressing discussion over the Ethereum blockchain's inability to scale resurfaced, and many people started to run towards the other blockchains which offered more scalability. So the exorbitant prices which arise due to this inability to scale are just the tip of the iceberg. There are many more issues which are to be handled due to the inability to scale. So let's see how these issues are handled. So what is the scaling problem we were talking about? So scaling is nothing but increasing the speed and throughput of the amount of transactions. So these issues arise when the amount of data passing through the blockchain has hits a limitation due to the insufficient capacities of the blockchain. So this will eventually drive up the cost of using the network, creating a need of scaling solutions. So there are multiple solutions being researched as of now, and they all aim for the same goal, that is scaling up the blockchain. So why is the scaling up blockchain hard? This can be explained using the blockchain trilemma. The theory of blockchain trilemma states that there is always a trade-off between decentralization, security, and scalability. To achieve one, the other two must be compromised to a certain extent. So, hence the scaling of blockchain without affecting the decentralization and security offered by the blockchain, which stand as the definitions of the blockchain, is hard. There are several researches going on to tackle this aspect. Until now, some have come up with some brilliant solutions. So, let's check them out. Some of you can say that to increase the computational throughput of the blockchain, we could have just simply increased the size of the block so that much more computation can be carried out by a single block itself. So it is not that easy because to store the data of a single city, we would need terabyte blocks, which is practically impossible as of now. So we will need scalable solutions so to implement higher throughput. What are the scaling solutions? So currently you can find four different kinds of solutions under development to solve the scaling problem. But interestingly, we can categorize all of them into four distinct categories. Each category proposes unique ways in which we can achieve scaling. These are the four types of solutions which have been developed. The first layer scalability solutions, second layer scalability solutions, scalable consensus mechanisms, and scalable distributed ledgers. Let's see this what scalability solutions basically the second layer offer and how they are implemented. So what is layer 2 scaling? To answer this question, we must have a small understanding of what are layer 1 solutions. Uh, First layer solutions focus on changing the code base of the main blockchain network, hence are referred to as on-chain solutions. These may seem trivial to some of you, so they may not be some more interesting. So let's dive deeply into the second layer solutions, which are far more interesting. These are often referred to as off-chain solutions. These are basically the secondary protocols developed over the main blockchain. These protocols would be the places for offloading transactions from the main blockchain to avoid congestion on the main blockchain. So these create additional spaces for transactions to be processed by outsourcing the execution of those transactions before reporting them back onto the underlying blockchain. So I've given a very oversimplified view of the second layer solutions. They are significantly complex than they sound. So even many thought even they are not possible. So humans are very ambitious and they have already implemented several layer 2 solutions. Like ETH 2.2 and synthetic optimistic rollups and many more. Let's see them on the further slides. So what are the existing layer 2 solutions? So there are many different layer 2 technologies and implementations of the second layer solutions which I've just mentioned, which provide solutions for scaling. So the common examples of these second layer solutions are evident in the form of state channels and off-site chains. So these are the two main implementations of the layer 2 solutions. The other implementations are plasma chains and rollups. So let's see them one by one. Uh, let's first check out the side chains. Uh, what are sidechains? Sidechains is an independent blockchain which runs parallel to the main chain, connected to the main chain via two-way peg protocol. So this two-way peg protocol allows the open transfer of cryptocurrency from the main chain to a layer 2 chain that requires a degree of third-party trust. So it is free to operate as a decoupled entity with their own behavior, consensus mechanisms, attributes, and their own security as well. So sidechains do not rely on the main blockchain security and are considered to be a little less secure. So this frees up the main chain to take on greater number of transactions, which is the main goal of our scaling. Some popular side chains are Polygon, Liquid Network for Bitcoins, and Shard chains for Ethereum. So how do they work? A user on the parent chain first has to send their coins to an output address where the coins become locked so that the user is unable to spend them elsewhere. So once the transaction has been completed, a confirmation is communicated across the chain, followed by a waiting period for extra security. This is also called a disputing time. So after the waiting period, the equivalent number of coins are released onto the sidechain, allowing the user to access and spend them there. So the reverse happens when he moves back the coins from the sidechain to the main chain. This is the pictorial representation of the process which I've just stated. Firstly, the user has to send their coins to the address mentioned on the main chain. So here the coins are logged and are verified, and then they are released onto the side chain where the transactions happen. And after the transactions happen, the remaining coins are further logged again, uh, and they're verified, and then are brought back onto the main chain. So this is the basic working of the sidechain. Uh, so, uh, so for the working of sidechains, we need something called federations. These are an intermediate group between the main and sidechains. They determine when the coins a user has used are locked up and released correctly. So this is the third party trust which I was talking about earlier. Now coming to the security, sidechains are responsible for their own safety. If there isn't enough mining power, it can be hacked. Since the sidechains are independent, the main chain would not be compromised even when the sidechains are hacked. This is the main reason why the assets are locked up in between. So the sidechains need their own miners. These miners can be incentivized through merged mining, whereby two separate cryptocurrencies based on the same algorithm are mined simultaneously. So what is the vision of the sidechains? Vision of sidechains is to imagine a global decentralized network of various blockchains, each with their own sets of rules, functionalities, and purposes that remain independent from each other yet form one seamless ecosystem. So this is the main vision of the sidechain. So now coming on to the plasma. Uh, plasma what are plasma chains? Plasma chains are a further step over the side chains. The working of plasma chains are pretty similar to that of side chains but are much more secure. It basically focuses on using the child chains that start from the original blockchain, with each child chain serving as an independent blockchain. So basically, each plasma child chain is a customizable smart contract that can be designed to work in a singular way, serving different needs. This means that the chain can coexist and operate independently. Eventually, a plasma will make it possible for businesses and companies to implement scalable solutions in various ways according to their specific context, interests, and needs. So, the child chain processes their own transactions while leveraging the benefits of security in the associated main chain. The independent operations of each child chain is in parallel to each other provides ideal opportunity for optimizing speed and efficiency. So the examples of plasma chains are Plasma from Ethereum and Polygon. So these derive their security through fraud proofs like optimistic rollups, and each child chain has its own mechanism of block validation. So so let us now look at the working of a plasma chain through this diagram. So in this case, if Alice keeps one Ethereum in plasma chain, for instance, it gets recorded into a blockchain, whereas the consensus is met due to fraud proofs. Further commitments are enforced and submitted on the base blockchain, and her funds are held in smart contracts. So she has to wait for the dispute resolution periods, like in the case of optimistic rollups, to get her assets back into the Ethereum blockchain. This may take up to 10 days, so this is one of the drawback. And Another drawback which you can see here is Plasma requires a centralized component in order to operate as off-chain component. It is managed by some authorities. This brings in a sense of some external centralization. So this is another drawback. Uh, So coming back to the fraud proofs which I've mentioned before, the communication between the child chain and the root chain is secured by fraud proofs like optimistic rollups. So the root chain is responsible for keeping the network secure and for punishing the malicious actors. The fraud proofs ensure that in case of malicious activity, users are able to report dishonest nodes, protect their funds, and exit the transactions. So each child chain has its own mechanisms of validating blocks of and a particular fraud proof implementation which can be built on top of different consensus algorithms. So the map reduce is the ability of the plasma chains to increase efficiency of the blockchain to very high levels. So the tree-like structures of the blockchain allows for the map reduce to be applied as a way to facilitate the verification of data within the tree of chains, which greatly increases the efficiency of the network. So the basically Plasma framework is built with smart contracts and Merkle trees, as we know, and this enables creation of unlimited number of side chains that can work to offload bandwidth from the parent chain, which are essentially smaller copies of the Ethereum blockchain. So uh, Plasma chains often encounter a problem called as the mass exit problem. So the mass exit problem is a scenario where many users try to exit the Plasma network at the same time, flooding the root chain and causing network congestion. So one of the main points of concern is this mass exit problem. This could be triggered by fraudulent activity, network attacks, or any other kind of critical failure that Plasma chain or a group of chains may present. So this is an issue which is to be tackled. So now comes state channels. So state channels help in enhancing the network efficiency and outcome when it comes to managing payment transactions. It does so by allowing multiple user accounts interested to transact their crypto using a direct communication channel which is off the chain. So state channels are a very broad, simple way to think about blockchain transactions and interactions which could occur on the blockchain, but instead get conducted off the blockchain without significantly increasing the risk of any participant. So this allows Ethereum applications to move transactions off chain, increasing the usefulness of the network as a whole. A state channel is a smart contract that enforce predefined rules for off-chain transactions. So each transaction creates new states based on the previous state. Each is signed by where each smart contract is signed by each party which is involved in the state channel, which is cryptographically provable on the blockchain. So every new state makes the last state invalid, since the smart contract acknowledges only the highest state as a valid state. So this is a basic definition of the state channel. Let us see how these work. So state channels work by locking up some portion of the blockchain state into multi-signature contract controlled by a defined set of participants. The state is locked up and is called the state deposit. Uh, After the state deposit is locked, the channel participants use off-chain messaging to use and assign valid Ethereum transactions without deploying them to the chain. So these transactions could be put on the chain anytime but are only put when the desired transactions are completed. So popular projects using these state channels are Raiden, Perun, and Sealer. Uh, so so steps that are inside the working of state channel, which I've just mentioned, is the first part is the part of blockchain is locked by multi-signature or some kind of smart contract, uh, so that specific set of participants must completely agree with each other to update it. So the second part is the off-chain transactions. Participant update the state among themselves by constructing us and signing the transactions that could be submitted to the blockchain at any time but are merely put held on to for now. Each new update trumps over the previous updates. So the after the completion of the transactions, finally the participants submit the state back to the blockchain, which closes the state channel and unlocks the state again, usually in a different configuration than it started with. So this is the state channel working. So we have seen a similar diagram in our slide earlier, we saw it in sidechain. So the working also seems pretty similar. Are they both same? So indeed they are not. These are the differences between the state channels and side chains. The privacy in state channels is strongly preserved as they use security measures of the main blockchain itself. Side chains use their own privacy and security measures. The parties in participation. So in state channels, always 100% of the participations is needed, but in side chains, only the sender has to be active. Participant movements into and outside the state channels is tedious because every time this happens, a new smart contract has to be uh, documented and has to be signed. In side chains, there is no such limitation. Longevity, side chains are permanent, whereas state channels are only short-lived till the purpose is solved. Security, as I mentioned before, in state channels, the security is maintained as the main blockchain, but in sidechains there are their own security measures. Initial investment in state channels is nothing, but for a sidechain, as they have their own implementations, a lot of initial investments is needed. Third party filtrations in state channels is not required, but in sidechains it is required. So now comes rollups, an interesting layer 2 solution. So what are these rollups? These are another scaling solutions that perform transaction execution outside the main chain, but once the transaction is through, the transaction data is imprinted on the layer 1. As the transaction data lies on layer 1, this allows rollups to be secured by layer 1 security measures itself. So the three key attributes of rollups are: the transaction execution happens outside layer 1, this re- reduces the gas fee; data or proof of transaction resides on layer 1, this maintains the security. A roll-up smart contract lying on layer 1 can enforce correct transaction executions on layer 2 by using the transaction data lying on layer 1 itself. So ultimately, roll-ups requires users like you and me to stake a bond in the roll-up smart contract, which encourages users to verify and execute transactions correctly. So so these rollups are very much useful because they reduce fees, increase the transaction throughput, and expands participation through incentivization. So the security measures are an important aspects of rollups as they determine the quality of transactions, which incentivize this the honest and punishes the fraud. So there are two kinds of rollups with different security measures. There are optimistic rollups which assume the transactions are valid by default and only runs computation via fraud proof in the act of challenge. So there are other kinds of rollups called zero knowledge rollups or ZK rollups, which runs computation of the chain and submits the validity proof of those transactions to the main chain. So these rollups help the blockchain to achieve the low transaction fee and open participation and fast transaction throughput, which are the basic goals of scalabilities. So this is the basic overview of optimistic and CQ rollups. There is no computation done on in the case of optimistic rollups, and our only computation is done on the main chain when there are challenges. In the case of ZK rollups, so the computations are done off chain, and a validity proof is submitted to the main chain for checking the validity of those computations. So let us check them out one by one. So uh, so optimistic rollups use fraud proofs. The main idea behind fraud proof is to send minimum data to layer 1 and assume that it is correct. In case of a transaction is valid, the blockchain transactions need not do anything. If it is invalid, it has to identify it, roll back the state, and penalize the sender. For achieving this, a dispute resolution system is used. It detects fraud activities, verifies fraud proofs, and de-incentivizes bad actors. This is done to prevent bad actors from spamming the network. The senders also have to submit a bond, usually in the form of ether. In case a fraud activity is detected in layer 1, this bond will be slashed as a penalty. This only happens in case someone challenges the proof of the transactions. So in optimistic rollups, long withdrawal periods, even in the form of weeks, are expected. This is mainly because all the network participants have to send the proofs before finalizing a transaction in layer 1. On the other hand, optimistic rollups are popular between developers mainly because the technology uses all the existing Ethereum tech stacks itself with little or no modifications. So let us see the working of an optimistic rollup through this in the illustration. There are two main components of in the case of optimistic rollup. There are aggregators and someone called validators, which are, who reside on the main chain. Once there are sufficient number of transactions, the aggregators put all these transactions in a block along with a bond, which they submit up to submit using a rollup contract. In the case that they provide an invalid transaction in this roll-up contract, their bond gets slashed as a penalty. So this slashing occurs only when there are challenges from the main chain. This usually happens in the dispute resolution period. So this is the basic working of an optimistic roll-up. So there are some pros and optimistic rollups come up with some pros and cons. The pros are low gas fees, increased throughput, smart contract capability, and security, which is guaranteed by the main blockchain itself. So the only disadvantage is a long withdrawal time, which is due to the challenge periods, which can last for weeks. So these lead to long withdrawal times only if the transactions are challenged. So the optimistic rollups based projects are optimism, boba, cartesi, fuel network, and the main hot topic which is on right now is arbitrum 1 is a protocol mainnet beta release. Right now it's only available to the app developers building on ethereum, but we will see a full public release very soon. So it is really happening, and arbitrum can really change the game of scaling. So that's it. uh, and now coming to ZK rollups. ZK rollups, in the case of ZK rollups, hundreds of transactions are bundled together off chain, and they are validated, and a cryptographic proof is generated. These proofs can come in the form of snarks or starks, and these are generally known as the validity proofs, and these get posted on layer 1. So ZK rollup smart contracts maintains the state of all transfers on layer 2, and the state can be only updated with the validity proof. This means that ZK rollups only need the validity proof instead of all of the transaction data. With a ZK rollup, validating a block is quicker and cheaper because less data is included. So with a ZK rollup, there are no delays when moving funds from layer 2 to layer 1, because validity proof is accepted by the ZK rollup contract, which has already been verified all the funds. So a zero knowledge proof approach is used to present and publicly record the validity of blocks on Ethereum blockchain. CK reduces computing and storage resources for validating the block by reducing the amount of data held in a transaction. Zero knowledge of the entire data is needed in this process. So this is basic property of ZK rollups. Now let's see the working. ZK rollups, in case of ZK rollups, it stores all addresses and respective balances in a Merkle tree. The root of this balance tree is stored on on-chain smart contract. When a batch is posted on-chain, a new Merkle root is proposed, which reflects the updated Merkle tree with updated balances from all the transfers that are included in the batch. The smart contract will verify a snark proof that's posted with this batch, and if it checks out, the new Merkle root is accepted and becomes a canonical state root of the contract. So all these are supported by zero knowledge proofs, which further add to privacy. So this is the working of a zero knowledge rollups. So these also come with some pros and cons. The advantages include near instant transfers. These are not vulnerable to the attacks that optimistic rollups may be affected by. These are still secure and decentralized. The disadvantages are the validity proofs are extreme to compute for smaller applications with less on-chain activity. A user can lose influence transaction ordering, and some rollups don't offer Ethereum virtual machine support, which is a huge drawback. So the applications of the ZK rollups application based on ZK rollups are MetaLabs, ZK Sync, and Starkware, etc. So these can be check them out. So optimistic versus ZK rollups. The delay time is very large in case of optimistic and nothing in case of ZK. Cost is a little cost in optimistic, but a medium cost per batch. The complexity is very less for optimistic, but it's high mathematical complexity is associated with the ZK rollups. Security mechanisms. These are vulnerable to attacks. The optimistic rollups are vulnerable to attacks, but ZK rollups are not vulnerable to economic attacks. So scaling potential is 10 to 100 times in case of optimistic rollups, and ZK rollups it's said to be in the range of 10 to 1000. So these are the so why is there need of so many scaling solutions? The multiple scaling solutions make the network more robust when it comes to handling failures in high traffic demand situations. It ensures speed, agility, and maximum availability. Different solutions can coexist and function in harmony, allowing for exponential effect on the future transactions, speed of the network, and throughput. Ethereum 2.0 using a suite of such scaling solutions. Um, no solution is enough for its grander 2.0 version. Also, multiple scaling solutions do support multiple consensus mechanisms that can be used based on specific use cases. So we wished that let there be speed, decentralization, and the security all coexist together to help the decentralized blockchain thrive and scale for good. So so my final thoughts on layer 2 scaling solutions is layer 2 scaling solutions are addressing the most important concerns of the Ethereum blockchain. They increase Ethereum's throughput, they decrease the verification latency, they significantly reduce transaction fee, and in case of rollups, they ensure high level of security by relying on the security of the main blockchain itself. So we are still in very early stages of adopting layer 2 scaling solutions. However, with layer 2 solutions, once ETH 2.0 is launched, the future of Ethereum blockchain is super. These layer 2 solutions have some serious potential to change the blockchain landscape for better and ensure that users are able to maintain all the safety measures used on the Ethereum mainnet while still being able to transact quickly with a little or no cost for users. So this type of technology may encourage more people to try out Ethereum blockchain and everything it has to offer. Also keep in mind that many layer 2 solutions are still in their beta phase, meaning that you should research everything in depth and always remain curious and cautious when exploring various layer 2 solutions. So this concludes my talk, and I really hope you enjoyed it and taken some interest in layer 2 solutions. Thank you.